Thank you very much for the introduction. It is a great pleasure and privilege to join you in today's symposium honoring Professor Al Oppenheim. I know Al is going to come to the room very soon. Two distinguished speakers before me have shared with you the needs and the profound impact of signal processing. I will share with you my perspective working in one of the youngest technical areas of the IEEE Signal Processing Society on information forensic and security, and also working with several of the society board and managing the IEEE Signal Processing magazine. Like many of you, I first know Al's names from textbook, being an undergraduate student learning signals and systems in Tsinghua University in Beijing. At the time, the publisher hasn't entered the Chinese market. There were only one copies in our library. You can imagine several hundreds of students sharing that. It's nearly impossible. But our instructors have used many very nice pedagogical examples from the book, from the way to explain the nice, the complex concept to us. And then I came to the States for my graduate study. We used this book, also by Oppenheim, and edited together with Professor Jay Lin, Advanced Topics in Signal Processing. This was contributed by several experts in the field. I really like the book. It gives us an exposure of a number of topics in signal processing, not in complex ways, but highlighting the key point for us to understand and appreciate. Considering many of today's curriculum in ECE that we take for granted, but many years ago, this was active research areas, and thanks to the effort from Oppenheim, they bring this to our students in very easily understandable ways, and also to many of the professionals, and giving us the signal processing knowledge and skills to deal with a variety of signals. And that's not at the end. More recently, our magazine editorial board has appreciated very much the MOOC effort from Oppenheim, and also he's teaming up with Martin and Rich Bruniok at Rice University to write these informative articles for the magazine published July last year. They shared their experiences through 3 universities in this MOOC effort, shared best practices, and also discussed what lessons learned, what worked, and what may be done better. I also learned Al's profound impact from the undergraduate studies from our faculty. This was after the ping-pong diplomacies, playing a key role in sorting the tensions between China and the US. And following that was the scholarly exchange. Including here at MIT, there were 9 scholars selected by the government to come to MIT. It sounds very easy today, but to put in the context, there were no Google scholars to assess their credentials. In fact, nearly 20 years of political turmoil just ended in China. International publications were never encouraged or even allowed. So in all the reasonable ways, there's no way to assess their credentials. So doubts is really reasonable by that. It would take courage to support giving those scholars a chance to try and be willing to serve as a host. And Al did just that. The scholar he hosted was Professor Yan Dali from Tsinghua University in Beijing. Professor Li had learned studied signal processing with Al's group from courses to taking part in research project. What he brought back to Tsinghua and to China had played an important role in developing signal processing education and research in China. And they later expanded to many of the areas, especially in the civilian use. Last year, Professor Li's research group and the signal processing colleagues he mentored had a gathering with more than 100 people. So if we were to extend that academic genealogy trees to also include visiting scholars for whose career and life that Al has such a profound impact on, as well as their descendant, we are going to see that tree of the expanded Oppenheim family to include many, many more names. Now let me move on to signals and talk about invisible signals. So most of my research dealing with nearly invisible signals I call it microsignals. Those are very small in terms of their strengths compared with the dominating signal, usually by at least one order of magnitude lower. And we are looking at a signal-to-noise ratio very low, usually minus 20 dB or even lower. And there are few examples that I could visualize for you that coming from the digital forensic and security applications. The first one represented the intrinsic microsignals representing the properties of imaging devices, such as how we handle the colors, what are the noise properties associated with those cameras. They are useful to provide us ways to determine how this image comes from, how it was acquired in the first place, from what type of cameras, whose cameras took a given picture, and whether there's any changes made on the picture in terms of the integrity. Another class of microsignals are associated with physical objects. Just like this piece of paper, different sheets or even different patches of that surfaces, in the microscopic levels, they are all unique. They are difficult to reproduce perfectly. So those are physically unclonable features, and they can serve as a unique fingerprint to help us discourage counterfeit and identify whether there's illicit duplications. So traditionally, we can capture those unique traces using laboratory equipment, very high-resolution scanners, cameras, or microscope. But today, everyday consumers, if we want to detect whether this is a counterfeit, especially in overseas markets, we only have cell phone cameras in my pocket. And those are uncontrolled environment and also consumer level devices. So one of the research questions we have been working on recently is to look at whether we can use those consumer level devices to be able to capture that microscopic unique signatures and then provide additional capabilities to counter forgery. The microsignals, we can also specially design them and then embed them into our hosting data as tracers. And this builds on robust data embedding, robust watermarking with additional properties that we want to be able to uniquely label each copy and also to be able to resist adversaries removal, whether they have one version or multiple versions. The examples I show here is applying that fingerprint to maps. And those maps can come from the data, the geospatial data, either on the land or on the ocean floor in terms of the terrain information. And while in the meantime to preserve the data fidelities. This top example, where microsignals are coming from our capturing environment, and that's what we are working on recently, and I'm going to tell you a few more things about that. So what you're seeing here is a visualization of the electrical network frequencies. So basically our power main, the frequencies on the nominal is 60 hertz in North America and 50 hertz in Asia, Europe, and most other parts of the world. If we're going to tap into our power outlet at any given time, it's not exactly 50 or 60 hertz, but it's varying slowly. In this spectrogram, horizontal axis is the frequency, vertical axis is the time. You can see they are changing. And this is actually a reflection of the dynamic process between our ever-changing demand for electricity and the power generation and the control mechanism in the grid to work and meet our demands. During this process, we have observed these variations. And depending on the capability of power generation and the control mechanisms, in here in North America, you see very little wiggles, but in other parts of the world, it can be more profound. Now, why this is important? You can see this can be modeled as a random process. It's associated with time. And another property we learned from power engineering community is anywhere in the same grid, the major trends of the variation is the same, which means from Maryland, where I come from, to New York City, to here Cambridge, to Florida, we're all on the same eastern grid, so we all share the same variations of that major trends. But at any given time, we're different from the West Coast, and you know Texas is always special. So this is a signal that can help us relate with time and location of sensor recordings, including media, video, and sound recordings. Now, to appreciate why that time and location are important, I like to bring up him. To think of the video propaganda of bin Laden, many people fighting terrorists want to know when the video was shot, where the video was shot. There's a soundtrack, there's a visual track. Are they captured at the same time, which means a certain intelligence information, or are they captured separately and then superimposed later? For answering this time and location question, it would be very difficult using the traditional security modalities. But if you model from the sensing perspectives, our recorders is a form of sensing. They work in the environment. They can be influenced by the environment we are doing the recordings. And this is where the signal processing coming from. And if you think of the sensors recordings, depending on the type, if our recorders are connected to the power outlet, there are profound electrical interference. It's small, but it's still measurable. Now, for many other work that our researcher was carrying out, we were using battery-powered devices. Even for that, depending on the sensor's modalities, they can be affected by the electromagnetic fields that our grid has really imposed around us, or by derivatives such as acoustic or mechanical vibrations that could be captured by the soundtrack. On the visual track where we worked on, you think of this room, we are doing the video recordings and we have lights. The lights are connected to the power grid. If we are looking at the videos frame by frame to look at that subtle changes in the overall brightness, part of it are contributed by these variations of the current applied to those lights. So if we are able to extract them, we visualize this time-domain analysis for you. And here on the right-hand side, that is variations that we extract from the visual track. So if those video and our reference recordings captured from the power outlet align at the same time, you are going to see the same wigglings. And doing this similarity check, when we align at the same time, we will see these strong similarities. So that is a basic idea. We can verify the time for this has been captured or estimated time. And in the same time, we're verifying whether it is coming from the same grid, because different grids have different variations. So in the early stages of the research, we were looking at how we can capture this from the visual track. Whether we can see this ENF from videos captured by the consumer level of camera. One of the difficulty we foresaw was the very limited frame rate. Typically, our consumer level cameras only 25 to 30 frames per second. Now, what are the signals we want to capture? The nominals were 50 or 60, but we also know the brightness is independent of the polarity of the current. So we're looking at this power law. The nominals for us to capture is 100 hertz or 120 hertz. So if we apply what we learned from Al's book, we have a significant lower sampling rate. So therefore, we have aliasing problems. And fortunately, there's no effective anti-aliasing filtering in that domain when we do this analysis. So using that sampling theorems, we can analyze where the alias come from. The base frequency, 100 hertz in a 50 hertz grid, will be aliased to just above 10 hertz. And then also, if there are harmonics, they are going to be analyzed similarly, have this mirroring effect. And that's indeed what we observe. If you look at that video I showed earlier, this was the 10 hertz alias to not 100 hertz. And when the harmonics were profound, we indeed see those mirroring and multiple copies consistent with the aliasing analysis. My colleagues had told me that they really like the research in one of the aspects that it shows to our students, both on the undergraduate and the graduate levels, how what we learn from the textbook and the courses can use to interpret those phenomena in research and other R&D effort. Of course, when you have motions, the brightness can change from frame to frame. And if you have newer sensors, CMOS sensors with rolling shutters, to extract this ENF will be much more involved. That will involve advanced image and video processing and statistical processing. So today, due to the time limitation, I won't go into details, but if we can extract these very weak traces, we can make sense of them to address questions about time and location. So if we have all this concurrent record for every grid, we will align with all the possible time or the possible grid of interest with which one we have the highest similarity. That will give us the time location information. But oftentimes in practice, we do not have the luxury to have all those records available, especially in new areas of interest. In investigations by law enforcement for child pornography, child exploitation, kidnapping cases, even the fact that we can help them to narrow down which region this was will help them advance the investigation. And when we visualize this, even without the concurrent matchings, you could see in Eastern grid, we are very, very flat. And India has some more fluctuations, and Lebanon has even more profound fluctuations. So this suggests that once we are able to use signal processing to extract that, we then can further extract features that we can cast under a pattern classification framework, and then infer what are the regions that most likely contributed to this recording. So here, visualizations of different features, starting from simple statistics to the wavelet analysis, which give us the statistics at different time scales and frequency bands, and also autoregressive modeling has been shown to be helpful. And you can see with proper feature domains, we can separate them and then address those region of capturing questions. And further, another intriguing questions would be where the recording happens within the grid. Can we do fine localizations? And that's much more difficult because the major trends of this has been shown to be the same anywhere in the same grid. And then we have experiment results showing up here from Maryland, Princeton, New Jersey, and Cambridge, Massachusetts. But if you look closer, there are those tiny differences that could be location dependent. So this is really a microsignal within microsignal problems. So what we have making progress is trying to analyze those tiny details. And if you look at those detailed trends of variations, we found that we actually can relate these pairwise similarities between the locations in that detailed trends with distance. And this is important because instead of doing this as a purely big data problems that we have to capture all the possible location of interest and only to compare with those and narrow down to those handful of locations, we actually can do this in a more scalable way. That is, we set up an anchor reference locations, at least 3 of them, more will be better, and we will compare the ENF similarities in that detailed trends of variation. And with a location of interest where we have the recording. And that will relate with distance. Once you have the distance estimate with multiple locations, we can do trilateralizations to do that localization. We are making progress along that line. And as an outreach effort, we have also adapted this simpler problems of region classifications to an undergraduate level of project. And this was adopted last year as the IEEE Signal Processing Cup topics, the Signal Processing Cup, and also the new acronyms VIP Cup for the topics in the visual domain was an outreach effort from a few years back by the IEEE Signal Processing Society as a vehicle to engage undergraduate students from around the world. So we are giving them topics that are coming from latest research and development with real-world application and impact, and encouraging them to apply what they learned from the courses along with other beneficial areas to tackle those problems. A total of over 1,000 students, undergraduate students from around the world has participated in this effort. Just last year alone, there are hundreds of students and dozens of the teams, and we give them not just computer exercise to implement algorithms, but each of them need to build a circuit to sense this signal, to analyze them, and make sense of them. And you also see from the finalist pictures, we have encouraging representations of female students. Some of the teams had a dominating number of females or as the leaders of the team. And we also see overall very strong performance in Southern Asian countries. Bangladesh, India, they are some of the winning teams of many of the signal processing cup. You can sense that enthusiasms, even though the research may not be indeed advanced, but with the opportunities, the students indeed shine. The ENF research also serves as a way to enable collaborations with social science colleagues. They were working with historical record now brought to digital domain. So this is under the umbrella of digital humanity. Interestingly, with the sound recordings, there are many of them in the second half of 20th centuries. Many of them are magnetic tape recordings. The ENF is actually very profound. Just we didn't really pay attention to those. We treated them as noise before. But now we have that. We can utilize them, and we ask digital archivists to preserve them as much as possible. The example here is showing you how we can use that to help us restore distorted tape recording. Those are from Apollo 11 moon landing mission.
This is Apollo Control at 57 hours, 44 minutes. We've had no further reports.
The tape was significantly distorted during the recording time. You can see the pitch was very, very low. Traditionally, we are going to do either trial and error or use sophisticated speaker modelings to be able to do the restoration. But now we know the ENF, it serves as a pilot tone, so easily there, very clean, and you cannot see it, but we can use this spectrogram to visualize for you and use this as a reference to restore for you.
This is Apollo Control at 57 hours, 44 minutes. We've had no further reports from the crew to indicate whether or not Neil Armstrong and Buzz Aldrin have returned to the command module.
This ability to utilize the signal processing to extract signals very weak, and especially with some motions, and also inspired us to look at beyond security and forensics and apply to other type of microsignals. For example, to estimate heart rate from video. And for the static case, it was really thanks to two pioneering efforts here at MIT from Professor Picard's group and also Professor Bill Freeman's group. And you can see they amplify those subtle color changes from the facial color. So we are looking at this in a challenging cases where you have really profound movement. For example, running on a treadmill, can we have a touchless cases to estimate our heart rate and monitor our health conditions? And this is a result that we are extending what we learned from the ENF to this domain. And the basic idea is we are looking at the dominating motion. It will smear all these microsignals, but estimate that first, and then the residual will contain our microsignals in better signal-to-noise ratio, and the further research will estimate that in high accuracy within 1% of the error rate compared with the gold standard from the 50s using the chest belt. From all this collection of research on microsignal and analysis from my group and also other colleagues in other institutions, we really see the theory and the techniques from a number of areas beneficial to help us develop ways to model the problem and to develop solutions and also address fundamental questions. So from learning, communication, information theory, applied crypto for the security problem, and also echoing Martin, the physics and the physical insights were important. In this and many other research and development areas that I interacted with colleagues through the magazine effort, we see a common theme that there are boundaries between the traditionally separated fields, even within EECS, has been so much blurred. The synergy between many many beneficial areas really enable new capabilities. We also see this from the evolved technical scope of the IEEE Signal Processing Society in terms of the number and the type of technical committees. In the 70s, you can see mostly one-dimensional signal processings, and in that are difficult and have a lot of advances. In the 80s, multi-dimensional signal processing are on the rise and have a lot of growth. Now we have many application areas with biomedical signal processing for communications, in machine learning, and language also brought into speech, and of course with information security and forensics. So in that area, we call it IFS. It's a rewarding effort to show that how the IEEE Signal Processing Society has embraced the new cross-disciplinary area. Traditionally, if you think of security, it's never in the scope of traditional signal processing. But back to the mid-1990s, with all the advancements on the digital technologies, we see the need to protect intellectual property in the digital domain. Digital watermarking, including the pioneering effort here at MIT and by other researchers around the world, had generated the global interest into the security problems. So thanks to the visionary effort and leadership of my colleague, Ray Liu, who was on the board, and the Society President Fred Mintz at the time, they found that we should not just go into a niche area of media security, but we really need three-pillar approaches to establish this community building to a broader domains. So with the three pillars, the technical committees for community building, a premier journal, and also workshop conferences. And we also have renowned experts, each leading the pillars. So we now, after 10 plus years, we have a premier journal, the Transaction on Information Forensics and Securities, having very significant citation impact. And it's really bringing people together. Otherwise, we are going to scatter around. But now, we have media security as a strength area, but also embrace many others from physical layers, communications, cyber-physical, sensor security, hardware securities, applied crypto, and biometrics. So there are many other similar areas and opportunities. We have imaging that Martin has mentioned, but data science and signal science is an area that we see growth. So my signal processing colleagues, Walter Kellerman, is leading the society effort, coordinating, and Jose Mura have been leading both on the society and IEEE level to let our signal processing community to embrace that and take the leadership of that. So what we have seen in the things that we're going to continue, the signal processing as a tool, as the fundamental principles really will continue to position, to contribute to breakthroughs in many disciplines. I did include with Martin, but both of us noticed this advanced imaging contributed to so many Nobel Prize. And I extended the notion of algorithm as a new literacy from Jim Tome at MathWorks, and I wrote an editorial arguing signal processing should be the new literacy because data analytics, signal analytics contribute to fundamental foundations in the STEM area. And of course, educating and mentoring to attract young minds to our field, including women and underrepresented groups. And by that note, I want to add my appreciation to Elle, that you have a trailblazing effort to nurture and placing one of the first women faculty, Professor Avida Zakor, on the university faculties. And seeing their success really encouraged me to pursue academic career. And also to you, Nina. I have been amazed by how well you balance work and life, and also break the ceiling to be the first woman winning the Signal Processing Technical Achievement Award. That's a fantastic contributions and a milestone. And we also need to educate our general public, including our young kids, about the roles and impact of signal processing. Our society president, Rob Ward, were championing the effort through short videos introducing the signal processing to them. and of course, collaboration around across the nation's boundary. So to sum up, signals can be invisible. You saw the examples I given to you earlier, and the signal processing may be inside and not seen by the outside world. In many new opportunities may not be in our traditional purview. It takes the courage, it takes a vision to embrace them and to encourage our whole village to join us. So in terms of the future of signal processing, it counts on our collective effort to strengthen and expand the scope and reach, to share and educate the general public of signal processing contributions as the science behind our digital life. That's the punchline of the signal processing societies now, and to encourage and attract young minds, and also to bring the community together to advance together. So I will end with this gallery of cover images from the IEEE Signal Processing magazines and show my appreciations and thank Al for the encouraging feedback, for contributing articles, as well as the effort from many of you contributing to the magazines in today's audience. Thank you so much.